Welcome to Scanning Thermal Microscopy Basics. In this three-part presentation, you will learn about an exciting new measurement technique used for the thermal characterization of samples at the nanoscale. The first part of this presentation will cover the basic concepts and principles behind thermal microscopy. This presentation has been brought to you by PicoCal and has been written by Amar Basu and Angelo Gaitis. Scanning thermal microscopy is a measurement technique which allows thermal measurements at very small length scales, at the nanoscale. These types of thermal measurements can include temperature. They can include thermal properties of materials such as thermal conductivity, heat capacity, and optical absorption coefficients. And it can also include thermodynamic or calorimetric analysis, such as glass transition temperature, latent heats, and enthalpy. What really distinguishes scanning thermal microscopy from other forms of thermal analysis is its high spatial resolution. As a basis of comparison, scanning thermocouple probes, which are formed by two dissimilar metal wires connected into a ball junction, this has a spatial resolution of about 50 micrometers. Infrared microscopy is a non-contact technique where infrared light is shined upon the sample in order to obtain thermal measurements and measuring thermal properties. This is limited by the diffraction of the wavelength of light, and it is typically limited to 3 to 10 microns in spatial resolution. Laser reflectance thermometry and micro-Raman thermometry are two techniques which have been more recently developed and have brought spatial resolutions down to 1 micrometer. Scanning thermal microscopy is about 1 order of magnitude better than the existing techniques out there, and it can achieve the sub-100 nanometer length scale. Being able to thermally image samples at these length scales turns out to be very important in the nanoscale characterization of materials and in the thermal analysis of semiconductors, for example, hotspot detection. In order to understand scanning thermal microscopy, we must first understand its predecessor, atomic force microscopy. SThM, as it's better known, is a scanning probe technique for the topographical imaging of samples. SThM probes can image surfaces with spatial resolution down to 1 to 10 nanometers. This slide shows how atomic force microscopy works. The basic idea behind SThM is to raster scan a sharp tip across the surface of the sample, essentially feeling out the topography of the sample. How it's implemented is that there is a sharp tip mounted on a cantilever beam which is attached to a piezoelectric actuator. This piezoelectric actuator can be moved up and down very sensitively by using a servo control voltage, V0. A laser beam is reflected off the end of the cantilever beam, just above the probe tip, and the reflected signal is aligned into a photodetector, a position-sensitive photodetector. Now, if the cantilever is deflected by the sample, this is going to cause the laser beam to be reflected onto a different portion of the photodetector. What this means is it allows us to measure deflection of the cantilever very, very sensitively. In fact, it can do so on the order of angstroms or nanometers. In order to image the topography of the sample, the probe is lowered to the surface. Here we have a sample here with bumps representing the non-uniform surface, and the system is operated in a servo control mode. The laser is again bounced off the cantilever into the photodetector, except this time the piezoelectric actuator is operated in servo control mode, and it is the servo signal is from the photodetector. So essentially, the voltage to control the actuator will be set such that the laser position on the photodetector remains the same. In other words, the cantilever deflection will remain at the same angle. So let's see what happens here. As over the course of the scan, the piezoelectric actuator will cause the probe to follow the surface of the sample. This prevents damage to the sample and also gives linearity to the signal that is produced. The output signal V0 represents the topography of the sample. Thermal microscopy works not by the mechanical interactions between the tip and the sample, but rather by the thermal interactions. Other than that, it's very similar to atomic force microscopy. When one of these sharp tips from an AFM probe or a thermal probe is placed in contact with the sample, heat flows between the tip and the sample. As the probe is scanned, the amount of heat flow will change, which in turn will change the tip temperature. So during the course of the scan, by monitoring the tip temperature, we can create a thermal map of the sample. The temperature interactions, the heat flow between the probe tip and the sample, depends on a number of factors, including the tip temperature, the contact pressure, and the contact area that is joining the probe tip and the sample, and upon the sample properties as well, such as sample temperature, thermal conductance, and heat capacity. There are many techniques which can be used in order to separate or isolate one of these factors from mechanical interactions as well. Just as an example, the degree of heat flow will change the tip temperature, which can be measured using an onboard thermometer. And just to show two examples here, one is where we have a low thermal conductivity material or a high temperature material. In this case, heat will flow from the tip into the sample, but there will not be as much heat flow. In this case, we have a hotter tip. Contrast that with the case where we have a high thermal conductivity or low temperature material. In this case, there will be increased heat flow between the tip and the sample. This results in a cooler tip. If we look closely at the mechanisms for tip sample heat transfer, we'll see that there's four ways that heat is transferred. The first one is what was talked about earlier. This is solid-solid conduction. Essentially, heat is being transferred from the apex of the probe tip into the sample. This is the transfer mechanism which we want, and this is going to be the transfer mechanism which yields the information in a thermal scan. Unfortunately, there are also three other forms of heat transfer which reduces the resolution of this technique. The first of this is liquid-liquid conduction. If we're scanning in a non-zero humidity environment, a liquid meniscus will form between the probe tip and the sample. Essentially, a tiny droplet will form right at the tip of the probe near the sample. With this liquid, conduction can occur through this liquid drop, as shown by the arrows here. And this, as you can see, will decrease the spatial resolution of the scan. Gas conduction is another factor. Through the lateral edges of the probe tip, heat can be transferred through the thin air gap that's separating the probe tip from the sample. This can also occur from the cantilever on which the tip is mounted. This type of conduction can be avoided by scanning under vacuum conditions. Number two, liquid-liquid conduction can also be avoided by scanning under vacuum conditions. And the fourth is near-field radiation. This is simply heat transfer via black body radiation. It is proportional to the Stefan-Boltzmann constant and is also proportional to the temperature cubed. As it turns out, near-field radiation is insignificant under most scanning conditions. In addition to the heat transfer between the tip and the sample, there are also other mechanisms of heat loss which involves the cantilever. One is that there is heat loss to the substrate via solid conduction. A heated tip will cause a thermal gradient to form over the length of the cantilever, and there will be heat flow from the tip into the substrate. Ideally, we'd like all the heat flow to occur between the tip and the sample, but unfortunately this is physically impossible. So we must be careful about the design of the probe in order to minimize this heat flow going through the cantilever. Another form of heat loss is from the cantilever into the substrate, as shown by the purple arrows. Again, since the cantilever is heated up, there can be heat transfer from the gap through the gap separating the cantilever from the sample. This also reduces the thermal sensitivity of the system. A simple thermal model can be used to account for the various types of heat transfer mechanisms between the probe tip and the sample and the cantilever and the sample. This model consists of an electrical equivalent circuit with three nodes representing the chip temperature, the tip temperature, and the sample temperature, respectively. They are separated by two resistances representing the thermal resistance of the cantilever and the thermal resistance of the tip-sample interaction. For optimal sensitivity, the cantilever thermal resistance should be much greater than the tip sample resistance. And for optimum resolution, the tip sample resistance should be the dominant heat transfer mechanism in the system. This simple thermal model allows designers a way to ensure that maximum sensitivity and resolution is achieved. This concludes part 1 of the presentation. Please continue to part 2 to learn more about the different types of scanning thermal probes and readout circuitry.